Alright, so our group did the liquid storage tank monitoring system, and we are the embedded engineering company for Team 23. This is for Professor Dr. Tiahi for the University of Cincinnati. The class is EECE4038C, and this is the fall semester of 2021. I'm Cole Tretchell.
I'm Caden Truby.
And I'm Jake Parker.
Right, so for the agenda, basically to give you a rundown, we're just going to go through the abstract, some objectives, a background introduction, and then we'll get into the block diagram, the working principle, flowchart logic, and then down through our Gantt chart, and then eventually hit the conclusion.
So for the abstract, EEC has created a project where a liquid storage tank includes a self-monitoring system. When any fluctuations in the tank's conditions occur, a user display provides the appropriate details and alarms the trigger, alerting the operator that an issue has ensued. A water level sensor, temperature sensor, humidity sensor, and tilt switch are used to monitor conditions. A LCD screen, audio device, and red LED are used to display tank conditions and certain alarms. This functionality helps regulate a tank's internal climate for any sort of sensitive or general liquid storage / dispensing application.
Alright, so for the project objectives, number one, we had to plan out the hardware and software designs for the embedded system. This included block diagrams for data flow, a detailed hardware drawing, and flowchart logic. Number two, we had to integrate the hardware components and secure everything in desirable locations to create like a shell-like system after the parts had been acquired. For number three, we had to develop and upload software that would take all the sensor inputs, deliver monitoring information to the LCD, and trigger output alarms when the tank's necessary conditions are not met. And then finally, for number four, we had to perform system I/O testing to verify the functionality, and then design refinement as needed.
Just a little background, self-monitoring systems typically provide constant feedback without the need to regularly assess the device. Most of these systems also have a way of locating exact cause so that the device can be easily looked at and apprehended. The liquid inside these tanks could be something simple as water, which is what we went with, or even something hazardous. You can see the most common applications in tank gouging, which is the measurement of liquids in large storage tanks with the purpose of quantifying volume and mass. This brings about the need for engineering standards and best practices to make sure everything is regulated and works correctly.
The goal of our project was to create an affordable embedded system that meets and exceeds the specs of current liquid monitoring tanks. With temperature, humidity, angle, and liquid level monitoring, the potential outcomes of our team solutions are endless. Our solution is appropriate because it is extremely cheap for clients, uses commonly used parts, can carefully monitor and maintain a variety of liquids, and can be customized for any application.
Alright, so the problem was to create an affordable embedded system that meets and exceeds the specs of current liquid monitoring tanks. So for the block diagram, we had a reset switch as an input. The other four inputs included a water level sensor, temperature sensor, humidity sensor, and tilt switch. And then for the outputs, we had an LCD, audio device, and red LED. The working principle for our project. A push button would set the system into a reset state. The microcontroller would take in water level, temperature, humidity, and tilt switch inputs. And then if the temperature was too high or low, humidity was too high or low, or the tank was not standing like vertical, an audio signal would play. If the water level in the tank was too low, then a red LED would light up, and at all times the LCD would display the water level tilt of the tank temperature and humidity. For the flowchart logic, we used C logic and downloaded it to the microcontroller using MPLAB IDE, and we used over a dozen functions to implement all of the logic. So if you work through the logic, it started out reading the humidity sensor, then the temperature sensor, tilt switch, and water level sensor, and then it would write the humidity, all of that data to the LCD. Then next, it would check if the humidity was too high or low, temperature was too high or low, or the tank was not level. And if any of those occurred, it would play a tune on an audio device. And then finally, it would check the liquid level. If the liquid level was too high, then the LED would turn, or if the liquid level was at like the correct height, the LED would turn off, but if it was too low, it would turn on.
So for the outcomes, the overall methodology was split into 4 phases: design, hardware integration, software, and then testing or troubleshooting, which roughly follows the engineering design process where the project is tapped to produce an optimal outcome. With the temperature, humidity, angle, and liquid level monitoring, potential outcomes of this embedded solution are endless. Private clients can purchase these tanks for controlled liquid storage, or local governments could buy them for water treatment plants as well.
For the results, the system was completed on time due to immense work from the EEC team. All 4 project objectives were met. The embedded system passed the I/O check after the team tested it up against the flowchart logic. The project successfully demonstrated on November 29th, 2021. So here is our timeline, or our Gantt chart. As you can see, it took a couple weeks, and here's all of our tasks in order from when we did them. And here's our budget. It totals $48. We only needed 3 pieces, which we have part numbers for and the part name. We had used a roll duct tape, a plastic cup, and the sensor kit. Part 1 was used to attach the sensors and actuators to the model. Part 2 is used to contain the water and used as a prototype tank. And Part 3 contains the sensors that were used in the system.
Alright, to wrap everything up, our company has found a better way to better regulate liquid storage tanks, and we've set forth multiple forms of data, as mentioned before, temperature, humidity, etc. Our next steps include preparing the project for production. Each tank will be specialized depending on the size needed, and then the liquid to be stored and variables to be monitored. One lesson learned is that for a project to be completed before an end date, it is really imperative to stick to the project timeline. Also, research is heavily important for a project of this scale. Simply attacking it without a plan can lead to confusion and potential loss of progress. So thank you. That wraps up our video and our presentation.